Today we're going to talk about a few more combinatorial games. We'll start with some examples of subtraction games, just like the 21 flags game. For our first example, we'll use a subtraction set of 1, 2, and 5. That means that players will alternate turns, and at each turn, a player can subtract either 1, 2, or 5 from the existing total. The question is, what are the p positions and what are the n positions? In other words, if we started with a stack of 21 coins, for example, who would win? If we started with a stack of n coins in general, for which n would player 1 win and for which n would player 2 win? We can answer that by just identifying the p positions and the n positions. And I'll remind you of what we've talked about before. We can characterize p position and n positions in the following way. First, all terminal positions must be p positions. This is using what we've been calling normal gameplay. With normal gameplay, the last person to move wins, and that means that a terminal position is a p position where the previous player, the one who made that last move, is the winner. In this case, that's just 0. When we get down to 0, we have to stop. So I'm putting a p there. We are going to identify for each other position possible in the game, whether it's an n position or a p position, in the following way. From every n position, there has to be at least one move to a p position. And in fact, any position where you can make a single move and get to a p position is an n position. That's one where the next player will win, because the next player can choose to just make that move to a p position and then continue on in this manner, and it will be a win for that player. So what are the n positions? Well, right now we can identify immediately with a subtraction set of 1, 2, and 5 that 1 is an n position. 2, that's also an n position, because you can make one move and get to 0, which is a p position. Also 5 is an n position, because the player can just take all 5 and get to a p position. Now, there are no other positions where a single move will lead to that p position, so we want to see if there are any other p positions. Well, how do we find a p position? From every p position, every move has to lead to an n position. So let's look at 3 here. If there are 3 coins left, and this is a subtraction game, where you can subtract either 1, 2, or 5, subtracting 1 gets to 2, that's an n position. Subtracting 2 gets to 1, that's an n position. And it's not possible to subtract 5. So that's a p position, because every possible move leads to an n position. What can we then say about 4? Well, 4, a subtraction of just 1 will lead to this p position, so 4 becomes then an n position. We can identify other n positions as well. We already have 5 as an n position. We could go all the way up here and say that 8 is an n position. But now we have to look for more p positions, so let's look at 6. Subtracting 1 gets to 5, subtracting 2 gets to 4, and subtracting 5 gets to 1. Those are all n's, so 6 is a p position. We can then just continue this process. 7 is an n position, because subtracting 1 gets to 6. 8 is an n position, and if we want, we can jump all the way up here to 11 and call that an n position as well, since subtracting 5 gets you to 6. And we'll just continue this process. I won't explain every little detail now, and we'll fill in the p there and the n there, and another, n here, and then we'll get another p here and an n here, and it'll just keep going. So continuing in this way, we can identify every possible position as p or n. Here's a question for you. Can we tell ahead now from this list what are p positions and what are n positions? Well, of course, we can tell for the numbers 0 through 14, but can we guess a pattern? The pattern should be pretty obvious, and I'll make the claim here. If the number n is congruent to 0 mod 3, And let me explain that. We're going to talk about congruence classes mod 3. That means the remainder when divided by 3 is 0. We say a number a is congruent to b if the difference, a minus b, is divisible by 3. So n is congruent to 0 mod 3 if the difference, n minus 0, is divisible by 3. That's the same as saying the remainder when divided by 3, when you divide n by 3, is 0. If n is congruent to 0 mod 3, then n is a p position. And if n is not congruent to 0 mod 3, that means it's congruent to either 1 or 2 mod 3. That means the remainder when you divide n by 3 is 1 or 2. That's the same as just saying it's not divisible by 3. Then n is an n position. So I'm claiming that this pattern we see here continues forever. Is this something we can prove mathematically? The answer is yes. There's a simple proof by induction. And since this isn't a real proof-oriented course, I still want to be able to explain how a proof by induction would go, but I'm not going to worry you by writing down all the details. For those, most of you are math majors. I know not everybody in the course is a math major, but certainly for math majors, try to be clear on how you would actually write down all the details of an induction proof like this. We start with the base case. And for the base case, we're going to be treating everything in groups of 3. So for that first group of 3, the claim is true. You can just check that in this first group of 3, the number congruent to 0 mod 3 is a p position, and the other 2 are n positions. And then we're going to go group by group, and we'll say if the statement is true for this group, let's say you know it's a p and n in this group, and all previous groups. So it's going to be a form of strong induction. If the statement is true for all previous groups, why will it be true for this new group? Well, let's start with the first element of this new group. Look at all the possible moves from that new first element. Subtracting 1 gets us here to an n, the last of the previous group. Subtracting 2 gets us to this other n, and that will be true not just for the numbers 12, 13, 14, but whichever group of 3 I'm talking about. So subtracting 1 or 2, or if we go back 5, we'll be down to here from 12. Those will all lead to n's, regardless of how far up I go, as long as it was always true for the previous groups. So we're always going to get a p there at the beginning of a group of 3. And then we'll always get an n for the next number, because you can just make a legal move to the previous, to 1 less there. And we'll always get an n for the element after that, because you could always move, you can always take away 2 and get to the p that we've already identified. So that's our induction step, and it requires strong induction. If it's true for all the previous groups, really you only need it to be true for the 2 previous groups, but strong induction allows us to assume it's true for all previous groups. Then it's still true for the next group. And the idea is that then it's still true for, it's using that induction step over and over, still for the next group and next group and next group. And by the principle of mathematical induction, it's true for every group of 3. In other words, this claim is true for every natural number n. So we've identified all of the p positions and all of the n positions. If you play a subtraction game with this subtraction set, 1, 2, and 5, and you start with 205 coins, then immediately you can say 205 is not divisible by 3. So what does that say? That says it's an n position. There's a winning move for the next player. What is that winning move? You want to leave it in a p position, so you'd go down to a multiple of 3. What are your choices there? Well, 204 is divisible by 3. So you can take 1 coin away, leave 204 left, and that will leave your opponent in a p position. Let's look at a very similar but slightly different subtraction game, one with the subtraction set 2, 3, and 4. Well, now we have 2 terminal positions. If there are 0 coins left, obviously that's a terminal position. We'll label it as p. If there's one coin left, no more moves are possible, so that's also a P. Then we ask, is 2 a P or an N? Well, there's a legal move from 2 to get to that P position, down to 0 by subtracting 2, so that's an N position. 3, you can subtract 2 to get to this P, or you can subtract 3 to get to the other P, that doesn't matter. It's still an N. What about 4? You can subtract 3 to get to a P position, or 4 to a P position, so that's an N position. And what about 5? Well, you can subtract 4 to get to a P position, so that's also an N position. But there are no other numbers for which a single move will get us to one of these P's. So now we look for more P positions. What about 6? Is 6 a P position? Notice that if we subtract 2, 3, or 4, all of them, any one of them, we get to N positions. So that tells us 6 is a P position. And look at 7. If we subtract 2, 3, or 4, we would get to 5, 4, or 3. Those are all N positions, so 7 is also a P position. And then we keep arguing like that. 8, we can subtract 2 and get to a P position, so it's an N position. 9 is an N position because we can subtract 2 or 3 to get to a P. 10 is an N position, and 11 is an N position since you can subtract 4 and get to 7. And then we'll see, similar to what we saw before, you have a P position and a P position, since any move 2, 3, or 4 from 12 gets you to an N position, and the same is true from 13. And I claim that this pattern continues. How would we describe this pattern? Well, notice that we repeat in groups of 6. And what are the P positions? My claim is that P positions are those which are congruent to 0 or 1 mod 6. In other words, numbers that leave a remainder of 0 or 1 when divided by 6. Things like 0 and 1, 6 and 7, 12 and 13, etc. N positions are all of the rest. Those are ones that are congruent to 2, 3, 4, or 5 mod 6. And one could create an induction argument, just like with the previous game, to see that this claim is true for any natural number n.